Okay, good morning everyone, and welcome to the second to last week actually of this course. There are 6 lectures remaining, which means we're starting to see the end. So I think the way I see it is that we are going to do some more of this classical material that perhaps you've seen or perhaps you've not, in maybe 3-4 more lectures, and then hopefully we'll have time for some of this bonus material I promised you earlier. But also, of course, I try to put interesting remarks and interesting perspectives as we go along, as usual. So try to remember where we left off last time. So we were talking about zeros and singularities, zeros and poles, but also removable singularities and essential singularities. So let's remember what it meant. So if we have a function here, a complex value function, we have a point, in A, we set A, then we said that f has a 0 of order n. So I never really defined this very formally, what it meant to have order n, so I'll do it now. So order n at A, so this means that locally f of z is equal to, can be written as z minus a to the power n times g of z, where g of z is holomorphic in a neighborhood of a, and g of a is non-zero. So this is by definition what it means. So for example, so if this essentially means that f of z has a power series expansion, as we all know, it always has a power series expansion, where the first non-zero term is the one corresponding to z minus a to the n. So this is what it means. Okay, and then we said that if we have, also said that the function f has a 0 at infinity. Okay, if and only if, by definition, f of 1 over z has a 0 at 0. Okay, so we also said this. Now if we would, of course, assume that this set A is now in the extended complex plane and contains infinity. So we have this correspondence between these points in the extended complex plane, where you have infinity here, you have 0 here, and you have the correspondence being z goes to 1 over z ascending 0 to infinity and vice versa. Okay, so maybe I'll just draw like this. They correspond to each other. So there's nothing special about such a point. Okay, so remember that. And then we said that a function was meromorphic on A if it was analytic or homomorphic, except at a set of isolated singularities that are poles. Okay? So if you have a function which has an isolated singularity but which is not a pole, which is maybe an essential singularity, then it is not a meromorphic function by definition. Okay? And meromorphic functions are very nice objects. So you should think of this as the rational functions essentially on the Riemann sphere, on this extended sphere. So for example, Möbius transformations are meromorphic on the extended complex plane, as you can easily see. Okay, so we had 3 types of singularities. Okay, 3 types of singularities. Yeah, so it was the first one that was not really a singularity at all, which was the removable one, more of a philosophical nature. Then we had poles of order n, and then we have the essential singularity. And let us now first talk about these poles of order n and try to understand why they behave nicely and show that they have a Laurent series expansion. Okay, around this point, for those of you who know what it is. And yes, we will explain where we get this expansion from. So assume now in case 2. So study case 2 for a moment. So then we said that it has a pole of order n. So f has a pole of order n at A. Okay, this we said corresponded to 1 over f having a 0 of order n at A. Okay, so this was the definition, if you remember. You have a pole at a point if and only if 1 over the function has a 0 at that point. So this means, if we look up here, so it means that so 1 over f is equal to z minus a power n times g of z. The g of z is holomorphic, and g of a is not 0. Or otherwise put, or equivalently, we may say that if we look at 1 over z minus a to n times 1 over f of z, then this function will be, so this is equal to this g, right? And this will be holomorphic. Okay. In particular, this is holomorphic in a neighborhood of A. Okay, so this function is holomorphic. So if this function is holomorphic, then we know from previous lectures that this function here is equal to, so all of this is equal to some power series in the neighborhood of this. So it has a power series expansion. So this is equal to the sum of k from 0 to infinity of some ak z minus a to the k. Okay, so for some coefficients. So we proved this. Was it last time? Yeah, I think it was last time. So we proved this. So now, what does this? So what we would like to show is that there is some kind of expansion, but possibly with coefficients with negative k here for f. So now we have the coefficient, the normal power series expansion with only positive coefficients corresponding to k non-negative here for 1 over f times this thing. Okay, so now we have to remember that we can actually divide power series with each other. Right? So now we have to recall. So recall that we have division of power series, but this is possible. So we said earlier that we can multiply power series in some previous lecture. I said this, but we can actually also divide power series with each other. Right? So in particular, so simply what we do here is that if I have some function which is equal to, let me call it something else, p and q maybe, sum of ak z minus ak, and you have q of z which is equal to sum of dk z minus a k, then you can look at p of z over q of z, which is equal to, okay, so you write this sum again up here, but then you write down here, you write this as 1 plus the sum going from k equals now 1 to infinity, okay, of dk z minus a to the k. And then you remember this. You remember that 1 over 1 plus z is equal to 1 minus z plus z squared minus z cubed, and so on. Okay? And so what you get is that this thing here, so this thing equals, so first of all this is equal to the sum ak z minus a to the k from 0 to infinity, and then times all of this, so times 1 minus sum of dk from 1 to infinity, okay, z minus a to the k, plus sum Sorry? Is there a question?
And the denominator is B0, not 1.
Oh, yes, good. B0. Thank you. So it's B0. So this is equal to, so this is equal to 1 over B0.
Yeah, and there, and
times all of this.
Yeah. Okay.
Yeah, so I took out 1 over B0. Yeah, you're right. Absolutely. So it's equal to 1 over B0 times this, and sum of bk z minus a to the k squared, and plus etc. etc. Okay.
So it will be bk over b0 squared.
bk over b0 everywhere. Yes, you're right. Okay, so it is equal to bk over b0. Okay. Yes. Anyway, this is not going to ruin anything about the argument, because, okay, this is some constant. Okay, and then you have these coefficients, so all of them correspond to z minus a to the power k, where k is 0, 1, 2, 3. Okay, so it's non-negative. And then you have all of this, and then of course you're not going to try to, I'm not going to try to write down some expression for what the coefficients are, but it is clear that you can multiply together and collect all the coefficients. So this is equal to the sum of ck z minus a to k from 0 to infinity for some ck. Okay? That is clear. And I absolutely do not ask you to sort of what this is. But anyway, so what it means is that if you divide two power series, then you get a power series. Okay? And here I have the power series 1, and here I have a power series for, so I want f, and I have 1 over f. So I want to look at 1 over this power series. So this implies that f of z is equal to, so, sorry, 1 over, like this, times 1 over sum of ak z minus a to the k.
But the expansion of 1 over 1 plus z
Yes.
holds if the modulus of z is less than 1, right?
Yes.
So we will put this condition on the expansion on the whole qz.
Yeah, so for sure, I mean, anytime we have an expansion, it is not really assumed that it should hold in the entire plane. This happens only for entire functions. So
I mean, if
everything is local. Yeah.
Yes, I mean, if we put absolute value of qz is less than 1, this will be very small, right? Or maybe, I mean.
No, I mean, so this series will have a radius of convergence, which is okay. You can do it. So I don't remember exactly what the expression is, but this will be. Okay. So you have this, and this 1 over this thing was equal to some other power series. We don't care which one it is, but this is equal to 1 over z minus a to the n times sum of ck z minus a to k, where k goes from 0 to infinity. Okay? And now, the final step, now we see where this Laurent series expansion comes from. So hence, we see that f of z is equal to, and maybe I can write it like this, so it is a to minus n over z minus a to n, plus all these terms, and then plus, c, I should say c minus 1, ck z minus a to a k, where k goes from 0 to infinity. Okay, so we have this expansion for the function. So if you have a pole of order n, you see that you have this expansion here where the lowest order term here corresponds to this n. to k equals minus n.
The sum from k equals n to infinity, not from 0.
No, from 0.
Because we will.
So if you have infinitely many terms,
Yeah.
and then you divide everything by.
We iterated the n first terms out of the sum. If I understand what we.
No, so we divide everything by z minus a to the n.
Yeah. And we write it the first, so when we enter the sum, it becomes ck times z minus a power k minus n, right?
But so let me take, for example, this times 1 plus, or let me take z now equals 1 over z squared, 1 plus z squared plus z cubed plus. Okay, so this is equal to 1 over z squared plus 1 over z plus 1 plus z squared plus z cubed plus.
No.
So it starts at 0.
Yeah. There.
Yeah.
At the end. If we alter the factor outside the sum, it becomes the sum of ck times z minus a power k minus n, right?
Yes, but the ck
Yeah, so
is different from the ck.
Yeah, so of course I renamed this k.
Ah, okay.
Yeah.
Ah, okay.
So I renamed this k.
Okay.
Yeah.
The c here is different from the c of
Yes,
just using
it's
the
not
same
the
c,
same.
but it's not the same.
Yeah. So I mean, yeah. So what I'm trying to say is that it has some expansion. Okay.
Yeah.
You know, if you want.
But
Okay. Now I understood at least your point, but yes, of course. So I mean, since I have nothing concrete on these coefficients anyway,
Yeah.
and I'm trying to show that there exists such an expansion, I don't care about my relabeling. You know, I show there are such coefficients. But of course, yeah. If you want to keep track where this comes from, then yeah, this one is the one that was the first coefficients over there. Yeah, that's good. Okay. Yeah. So let me maybe address this this concern. So before we go on, so let's have this general remark. So first of all, so actually, okay. So let me address your question here about the radius of convergence. Right? So if you have p of z times 1 over q of z. No, okay. Actually, let me not do this. Let me do this later. Let me do something else. So let me recall the binomial theorem. So you all know the binomial theorem in elementary calculus, but I do want to point out that you have a version of the binomial theorem here to make this a little bit more rigorous. You have something to hold on to when you do these by series expansions. So if a is a complex number, and you want to consider, so binomial theorem is about considering such an expression, right? But now a is any complex number, okay? So it's not just an integer, it's not even just a real number, but it's any complex number. So then actually this is equal to what you would expect. And so on. So it's equal to this where a over n, well, yeah, a over n is defined to be a times a minus 1 times all the way to a minus n plus 1 over n vector. Okay, so it's equal to this. And now we wonder, so now we will soon come to your question, because your question was for 1 over 1 plus z to the power a. So we'll at least give a statement on where this converges. So this would correspond to a equals minus 1, right? And then we look at this coefficient, so radius of convergence. For radius of convergence, we are interested in this kind of thing, or an plus 1 over an. But anyway, you will see. So this kind of thing is equal to n plus 1 over a minus n, according to my notes, but I'm sure it's very elementary to see here. Okay? And this thing, where does this converge? Where n goes to infinity?
1.
Yeah, so we have n here, we have n here. So n goes to infinity, and we had absolute values, right? So it goes to plus 1. this goes to 1 as n goes to infinity. And what does this mean? So the radius of convergence was, I think, 1 over this thing, right? So anyway, the radius of convergence is equal to 1 for this thing. And this would hold if A is minus 1 in particular. So you would be able to get this formula. So I'm not giving a proof for anything of this statement, but this is something that I think you should be aware of and that you can use always in your work. So in exercises and problems. Just something a little bit, at least a regular statement to hold on to, right? When you work. So, what have we shown?
This
Yes.
it is an entire function.
So if this is an entire function, our radius of convergence is 1 over.
So it's not an entire.
No. So entire would correspond to r being infinity.
But this
Oh, you mean if a equals 1 or something?
this on the left side seems like an entire function.
Yeah, I agree. So if a equals 1, there is something fishy. So
If a is equal to 1, then the
yeah, then of
binomial
course.
becomes 0.
Sorry.
The binomial becomes 0 because we have a factor a minus 1, then at a is equal to 1, then all the binomial becomes 0. The expansion,
Yes.
then we have some 0 over 0 here, or the expansion just becomes
Yeah.
1 plus a.
Yeah, you're right. So okay, so the mystery is solved by saying that this expansion holds for z less than 1. So yeah, so actually, so you can have a function which is entire, but then you can write it as so you have a power series that coincides with it, but maybe on some small disk. They're not equal everywhere. But yeah, so exactly. So this identity holds for radius of convergence 1. So that is it. Okay.
I think for a equal 1,
Yeah.
since the rest of terms will be 0, then we can't use
This formula.
the ratio.
Yes,
I mean n over n plus 1, we will have it equal to 0.
Yeah, but so if a is 1, then what does this say? So then you see that this 1 plus z is equal to 1 plus z. This is what this says, which is true. And then we don't care about this somehow.
We can't use the
Yeah.
ratio test because
Yeah, we can't use the ratio test.
we can't use it when we have terms 0.
Yeah. No, that's exactly. So the formula still holds clearly. Yeah. Okay.
We can conclude that if a is not natural, then this function is not entire. Yes.
Yeah. Well,
In is not a n is not equal to 0, and then the radius is equal to 1.
mhm. Yeah. Well, okay. We can study this later. So this was intended as some parentheses. So, okay, maybe I should immediately write down the formal statement of Laurent series expansion. So, formal statement. So, okay, now we have seen how we can obtain such Laurent series expansions. But we have not gone through all the details to write down the following. So along these lines, we can generalize this slightly, and we get the following theorem. So on the Laurent expansion. Okay, so suppose that F is analytic, holomorphic. Okay. So now I'll actually write down a statement which is not even restricted to isolated singularities. So you can even have more than this. So suppose that it's analytic in an open annulus. So the open annulus will be, so you have A here. And then you have R0 and R1, these radii here. Okay? So this respective radii. So suppose it is analytic inside such an annulus. Okay? So if R0 is equal to 0, then you can pretend that this is an isolated singularity. And then it's defined everywhere. But even, there are non-isolated singularities. Can you think of an example of a non-isolated singularity, by the way? Yeah, so the logarithm has an entire axis or an entire curve of singularities, right? So then you would, you would have a non-isolated one. So in an open annulus, 0 less than, strictly less than R0. This is less than or equal to infinity. So R1 could also be infinity. So if R0 is 0 and R1 is infinity, then it's defined everywhere except in 0 and infinity. So in this open annulus. So let's assume this. Then F has a Laurent expansion. Around A. And it is of the form. So of course what we proved here now is that we can obtain this if we have a pole. Okay? So, but even if we don't have a pole, we just suppose it's analytic in such an annulus, then if you remember the little tricks, we had to prove that any holomorphic function has a power series expansion. We looked at this representation formulas and then 1 over z minus w, we expanded this, into a power series. So along these lines, you will get the following statement. You will get a series where the sum is from minus infinity to infinity. So here it was from minus n, where n was the order of the pole. Here it goes from minus infinity to infinity of ak, z minus 1 to the k, which converges at least, so it could converge in a larger set, but at least it converges for R0 for absolute values between R0 and R1. So at least it converges in this annulus. Okay? And we even have an expression for these coefficients. So AK is equal to 1 over 2 pi I. So of course you will understand where this comes from, right? This looks very much as what you get from this representation formula, dw. And this is true also for negative k. Okay. Q less than 0. So you can note that. And the singular part so here is a new word, right? So the singular part is the part with negative coefficients, okay? So the singular part, sum of k equals minus infinity to minus 1 of ak z minus a to k is analytic for absolute value greater than R0. So it's analytic everywhere far away from A. Okay? And this other part is analytic close to A, so with absolute value less than R1. Okay, so in particular, And this other part, k equals 0 to infinity, ak zk converges for absolute value of z minus a less than r1. And so, in particular, if you have an isolated singularity, this singular part converges everywhere away from the point. Okay? So this is the formal statement of the low-line expansion that you can get. And so, an important remark is that, so if you have a pole, then this singular part has a finite number of terms. It has a lowest term, which is the order of the pole. And you can actually, if you have the Laurent expansion in front of you of a function, you can actually see if it has a pole or isolated singularity at A by seeing if it has a finite number of terms in the singular part or if it has an infinite number of terms. So this actually characterizes this behavior. Okay, so maybe let me write that down. So remark, so the singular part has finitely many non-zero terms if and only if f has a pole of order n or a removable singularity. Okay, so a removable singularity would be if there are no non-zero terms in the singular part, or a removable singularity. Okay, so this is what you can immediately read off from the Laurent series expansion. So, in fact, a pole means, so to summarize, so if you have some holomorphic function in a neighborhood of A, then either, so there are three possibilities again, so either absolute value of z minus a to the r, f of z goes to 0 as z goes to a, okay, or absolute value of z, so for some real number r, okay, so this means that it is controlled in some sense by this z minus a to the r, kind of polynomial term. So this is quite nice. Or this thing goes to infinity as z goes to a, some against some r, and 3, none of the above. So this is obviously a very simple thing to prove, that I said that either 1 or 2 holds or none of them hold. So this is clearly true. I said nothing. Sorry? Now this goes to infinity. Oh, yeah. I think I said 0, but okay. Thank you. Yeah. So these first two would correspond to poles or removable singularities. Okay, they all fall into this first two categories, and this third one corresponds to the essential singularities. So this is when the function is somehow more wild than having this kind of behavior. Okay, so now I just want to discuss for a short while an example of a function with essential singularities and give you some idea of what this means, what happens if you are in none of the first statements. So you have an infinite number of terms in the singular part of the Laurent series, then a function is surprisingly wild. So, does someone have an example? Just in case. So I have an example that I want to take actually, but maybe you will say the same one that I want. Otherwise, I'll take the one I want anyway. Yes, very good, thank you. Okay. Excellent example. So, so f of z is equal to 1 over z, has an essential singularity at z equals 0. Okay, so how can we show that this has an essential singularity at 1 over 0?
We can use the expansion of e power z.
Yeah.
Against Aristotle with 1 over z.
Yeah. Yeah, that is correct. Okay. So, first of all, you can see that e to the 1 over z is equal to 1 plus 1 over z plus 1 over z squared times 1 over 2 factorial, and so on. So this is infinitely many terms. So you will understand from the claim here of the statement that it has to be an essential singularity. But from the definition, so this is sort of a claim. But let's prove it from the definition. So by definition, and going back to the definition, need to exclude the possibility that limit of f of z, where z goes to 0, okay, exists equal to infinity or a finite value, okay? But you know that if this limit exists and it is a finite value, like limit of sine z over z would be 1. Then it has a removable singularity by defining the function to be equal to this finite value in 0. And you become holomorphic. If having a pole means that this limit exists, but it is infinity. Okay? Like if you look at 1 over z, this is a function which has a pole of order 1. So this has a well-defined limit as z goes to 0. The limit is just infinity. It blows up. But then you have so you have to exclude these two possibilities, and then by definition, so essential singularity is defined to be a singularity that is not a pole and not removable. So to see this, consider simply zk is equal to 1 over k, where k is in n. This implies that e to the 1 over zk is equal to e to k, which goes to infinity as, let me write it like that, as zk goes to 0. So k goes to infinity, zk goes to 0. So if you approach 0 from the positive real axis, the limit is infinity. But of course, if you put zk instead equal to minus 1 over k, then this implies that e to the 1 over zk is equal to e to the minus k, which goes to 0 as zk goes to 0. Okay, so if you approach from the negative real axis side or positive real axis side, already you get two different limits. So the limit does not exist. Okay? Okay, on the other hand, there is a very peculiar thing that happens. So observation. Now, if I look at, so I want to study this function, so I write z on exponential form, or maybe on polar form. Okay. So I write it like this. Or what? Let me not write it like that yet. So then I get e to the 1 over z is equal to e to the 1 over r, e to the minus I theta. Okay. So this is equal to e to the 1 over r times, and then this one I can, if I want, I can write it as cosine of, I guess, minus theta plus I sine minus theta. Okay. So this, and if I look at the absolute value of this thing already, you see that the absolute value will be equal to e to the 1 over r cosine of minus theta. So you see that this absolute value can take any values from 0 to infinity. Okay, so yeah, let me continue here. Okay, so what I want to say is that this function can take any value w in C. Okay, so it can take any value. What?
Except for -1.
Yeah, but this one can take any value.
No, can you take
Well, except
0.
0, I guess. Yeah.
In the example, we show that e power minus k tends to 0.
Sorry.
We showed that as z decay tends to 0.
If what? Sorry. A. Zk tends to 0? No.
Yes, zk tends to 0.
Yeah.
E power 1 over 0 tends to 0.
Why? I mean, we saw here that it could tend to infinity or
No,
to 0.
second one.
Yeah, second one. Okay, so when you take minus 1 over k. Yeah.
Yes.
Yeah. So then it tends to 0. Yes.
So you are saying that e power 1 over z will take any value without limits, right? Or will
Well, no, I guess it cannot be 0 because it's the exponential, but
yes, I mean without limits, without taking limits.
yeah, without taking limits.
Yes.
Yeah, without taking limits. So the formal statements, actually, there is an amazing theorem about this. So in particular, you can note that, okay, it can take any value except 1, actually, but except possibly 1. But the statement here, so in particular, you can see that the image of this function is dense in C. So it can take almost any value, okay? So it's dense. And this is the Cassonati-Weierstrass theorem, says that this is in fact always the case. Weierstrass theorem. Okay, so this one says that if f has an essential singularity, sure. Has an essential singularity of A, z equals A, then for any r greater than 0, you can look at the image of the ball centered at, or the disk of radius r centered at A. Okay? A, the disk, and this radius is r, and you look at the image of this. So this can be very small, okay? As small as you want. So this, so it's obviously a set inside the complex numbers. So this is dense in C. Okay, so dense in the topological sense. Okay, so the topology of C, I repeat, is the topology of R2. Okay, so this image is very dense. This is remarkable. Okay, but if we look at this example, we can kind of believe it if we convince ourselves that this is the case here. But the remarkable part is, as soon as you have infinitely many terms in the Binomial expansion, in the singular part of Binomial expansion, I should say, then this must happen. Okay, so let's prove it. Let's give a proof by contradiction. So let's suppose not. Okay, so if we assume it's not dense, then it means that somewhere, of course, I just check what it means. It means that there is some W, okay, there is some point somewhere in C, and some disk around it with a small radius, okay, R prime, such that it contains no image of any point under this function. So no f of z is inside this disk. Okay. So then we can take this W in C such that okay, so we fix some epsilon, let's say. So then we can take W in C such that the absolute value of f of z minus this is greater than epsilon. For z in yes. Okay, so this picture is not exactly what I want, but okay, so we take this. So there is a function such that for any in a neighborhood of A, okay, so the R prime was in the neighborhood of A. So for any z inside this small neighborhood, this function does not approach. This function value does not approach W. Okay, so f of z minus W is greater than epsilon. Because what I wanted to prove is that for any R, this is dense. Okay? So the contradiction is then that, suppose not, then I can find some R prime such that the image of some sufficiently small disk is not dense. I mean, stays away from some special point W. So this is what I want to show. So now using this fact that this is greater than epsilon, what can we say? So we can look at this thing, and this goes to, so this is greater than epsilon, okay? So this goes to infinity now, under this assumption, as z goes to A. And now we will see that actually this will mean that we have to have a pole or a removable singularity in this point. Okay. So what does it mean? So what I just wrote means that the function g of z, which is defined as 1 over z minus a times f of z minus w, has a pole at z equals a. Okay? This is what it means. So, yeah, sometimes, by the way, sloppily you can say, so a removable singularity, sometimes you can sloppily include this in a pole. You know, instead of saying always pole or removable, you say just pole, and you view removable singularity as a pole of order 0. Okay? So it's not really a pole. Now this is a pole, So what does this mean? So f of z. So f of z is equal to g of z times z minus a plus this w here. Okay, and g of z had a pole of some order. So this means that it is equal to h of z over z minus a to k, or maybe n, with h of z analytic and n being the order of a pole, right? And yeah, h of z is 0, and n is order of the pole. This is not important, but just for the general frame. Okay, so n is this one. So now f of z. So what is f of z? So f of z is g of z times this plus w. So this is equal to h of z over z minus a n plus 1 and minus 1. Okay, yes. Okay, and minus 1 plus w. And this was just a constant, just any complex number. This is analytic. You divide by z minus a to some finite power. Okay, so clearly, if you take the Laurent series expansion of this, it has a finite number of terms. So f has a pole or a removable singularity at z equals a. Okay, and the order of this pole or singularity is n minus 1. So if n was equal to 1 here, then this would be 0, so it would be a pole of order 0, which would be a removable singularity, if we use this terminology. Okay, but it's a pole or a removable singularity at z equals a, and actually this finishes the theorem. So why? So we have shown, so suppose that this image is not dense, then we have found a small, a sufficiently small disk here, R prime. We have found a small disk such that f actually has a pole. So not an essential singularity. So this is a contradiction. And the conclusion is that we can never find such a small disk where f of z stays away from some w. And this actually means that the image is there. Okay, so we have this theorem. Then there are more advanced theorems of this kind saying that, okay, not only is this image dense, but it takes every value except possibly one infinitely many times. Theorems like that, called the Picard theorems. I will not do that today. I might do it later, of course. Okay, given time. But now we will go to a truly important part here. A truly nice part. So now we have shown this Laurent series expansion. Then actually it is very easy to prove the residue theorem. I don't actually know if every complex analysis course in the world proves the residue theorem, or if people just use it. I'm not even sure what happened in my first complex analysis course. I don't remember if we saw the proof there or not, or if I saw it later. But now we come to, of course, the important topic of residues. Okay. Okay, so residues. So now we take f some meromorphic function, or actually, so f is some function. So f of z is equal to this Laurent series expansion. It does not have to be a meromorphic function, of course. The residue theorem applies even if you don't have a pole. So you have this expansion with the singular part. So it is equal to, so you come here from minus infinity, and then you have a minus 2 over z minus a squared plus minus 1 over z minus a plus a0 plus a1 z minus a plus a2 z minus a squared, and so on. So you have this potentially infinitely many terms, and here you have infinitely many terms in general. So the residue, as I think you all know very well, is defined to be this term. Okay, 1 over a minus 1. So definition. So a minus 1 is defined to be the residue of f at the point A. Okay? So residue of f at A. Okay, so this is the definition. But somehow, why is this so important? This a minus 1. This is the question. So, as you all know, so this a minus 1, the residue, it will be very important to compute integrals, right? So you have all seen the residue theorem, so I will write it down in a minute, but just try to remember already now, the motivation part, that we said that the integral along some curve of some function is up to a multiple of 2 pi I. It's equal to the sum of the residues for the poles that are inside. Singularities inside. Okay, and this seems like a complete miracle. So you have this, I mean, at first glance it seems like a complete miracle, but there is an extremely good explanation for this, which is nice and important, and that I want to tell you now. So you have infinitely many terms. Why should this one be special? So 1 over z. Okay, and so I will continue right here. Why it is special? But let's just see. So if I take, let's say, a circle. So let's say I take a equal 0, maybe. And then I take this to be the circle. So gamma, which we said this be unit circle or something. Then what happens if I integrate 1 over z squared dz along this circle? Then what is this equal to? Aha, it's equal to 0. Why?
Because 1 over z squared has a primitive.
Exactly. So it's equal to 0 because 1 over z squared has a primitive. So 1 over z squared, you say, aha, but it has a singularity, it has a pole of order 2, actually, in z equals 0, but it has a primitive. So because it has a primitive, this is equal to just the value of a primitive in the two endpoints, but the path here, the curve is closed, so this is 0. So remember, and the same thing, of course, happens if I replace this with k, where k is not 1. Okay? So then I can do this. So k is not equal to 1. But, of course, if I take this integral, this is actually the only, so of all the integrals of this form, this is the only one that gives trouble. Well, okay. So if k equals 0, I guess this is also not true, but yeah, anyway. So we think of it. So if I take this integral, 1 over z, then what is this equal to? it is equal to 2 pi I, which is non-zero. And this is possible simply because, so 1 over z has no primitive in all of C star. Right? Because the primitive would be the logarithm, but we cannot define an analytic branch of the logarithm in all of C star. So I'm sure you looked at your homework also to try to get even stronger statements like this. Okay, so actually when I try to take the integral along such a thing of a sum, so let's say that I have such a sum. Okay, so what happens is in fact that when I integrate this, all the terms, so the terms that have k not equal to -1, okay, so if the terms that are, 1 over z minus a to the power 2, 3, 4, 5, 6, etc., they will all give no contribution to this integral because they have a primitive, okay? So this thing, so actually, okay, so let me write here now, instead of continuing my informal discussion, let me now continue with formal one. So this is enough. So then, yeah, okay, let me by the way say this, that the residue of f in A equals 0 if and only if you have a removable singularity, okay, this is my definition. But now let me say, so f of z minus this a minus 1 term, minus this a minus 1 over z minus a, of course. So if I take away this term, so then I'm left with all these terms except the one that has no primitive. Okay? Then this is equal to the sum k minus infinity to infinity, k is not equal to -1 of ak z minus a to k. And this is equal to, in fact, the derivative of the sum of k from minus infinity to infinity. K is not minus 1. Okay, of ak over k plus 1 z minus a to the k plus 1. Yeah. Okay?
Why are we allowed to interchange the derivative and the sum?
Exactly. So we have, so of course this is a delicate question, this is an important question. So we have seen previously that when we work with these power series defined by holomorphic functions, then they are actually, so they are uniformly convergent by the end test, and so you are allowed to interchange these things. So this is a discussion that we have touched upon a bit previously, if you remember. So this will be the reason. So actually when you have these power series, they are nice enough so that you can actually do it. So you know basic statement that if you have a uniformly convergent theory, you're allowed to.
But here we have also negative terms.
Yes. So then I need the statement from the Laurent, what I wrote when I wrote down here the Laurent series expansion theorem. I said that the singular part, so you can view it as the sum of two power series, right? So now it's just two things, and the integral of the sum of the two things is the integral of the sum. Okay? And each of them converge on this and on this, and each of them actually converge uniformly. So you will actually be able to do this. Okay? So, but of course, it's a very pertinent question. I mean, it's important to be able to justify this. The idea is that, so this is equal to the derivative of this sum. So this means that, so let's define this, let's take this part and define it, call it g of z. Okay? So this means okay, so if I integrate along, now let me take any path gamma, okay, gamma something, like this. A is here, or A is outside, whatever you want. So f of z minus a minus 1 z is equal to the integral of gamma of g prime of z, which is then equal to 0. Because it's this, so g of z is holomorphic. Okay? Or, well, yeah, I mean it is, it has a primitive, okay? So this is going to be 0. And now, so this, assuming of course that gamma is a closed curve, otherwise nothing works. The gamma is a closed curve. Now, this implies that, of course, if we just take this integral, so it follows immediately that this is equal to, so this was equal to 0. So integral of f is equal to the integral of this, okay? So it's equal to the integral of a minus 1 over z minus a dz in gamma, which is equal to a minus 1 of integral of dz over z minus a. And this was equal to 2 pi I. Is this correct?
No, the number of.
Yeah, so it's even in general it's equal to 2 pi I. That's a winding number.
We can suppose this one.
Exactly. Well, yeah, so almost always in applications this will be equal to 1. But in general, you remember this was actually, so when I told you here we were doing this example on the circle, then the winding number was 1. Okay. But if it winds several times around A, then you have to remember that there is this thing.
A minus 1?
Yeah, times I minus 1.
Yeah, that's it, minus 1. Times A minus 1. Right, so the only hypothesis we need here is that A is not on gamma. Then we can do this. Because if A is on gamma, then we don't know what this winding number should be. We have some problems with this. Okay, so what we now get is the infamous residue theorem, which is the highlight of any complex analysis course. So what we get is a residue theorem. Okay, so it says the following. So I simply connected yeah. Very interesting. Here I wrote the statement for meromorphic functions. But residue theorem is true, so is this just right? So obviously, okay, so what I wrote in my notes was obviously if you have a finite, so if you have a pole, okay? So if you have a pole, then this singular part, then you have no problems of convergence with that, and you have the convergence of the positive part, okay? So, yes, okay. Actually, since I want to check, let's assume that you have a pole. I'm very sorry about this. So let me assume that you have a pole in this proof. So this is a pole. So F is meromorphic. Then clearly this whole proof goes through. And let me check until next time, just to be sure. There is no delicacy. So A is simply connected. F is meromorphic. In A. With no, but I'm pretty sure this holds, right? I don't know why I wrote it down like this, but finite number of isolated singularities. With isolated singularities A1 with a finite number. Look at this hypothesis. Okay, with a finite number of isolated singularities A1 to AN in A. So let gamma be a closed curve. So of course, I mean, what you want is that you want all of these sums to converge, right? This is why you put these hypotheses. So you could have an infinite number of poles, but only a finite number of them are inside gamma, or such thing. And all of this will help, of course. So let gamma be a closed curve. Such that none of the AIs are on gamma. Then we get the statement that the integral of f of d dz is equal to 2 pi I times the sum of z in A of n of gamma z residue of f in z. Okay, so you get this statement. Okay? So, what are the hypotheses there for? They are there to assure, as I said, that everything converges and everything makes sense. Okay. So, I mean, if there are almost always in applications, you have some curve with a finite number of singularities inside your thing. Okay, inside your curve, and so all of this clearly converges. You have this statement. I am sure that this statement can sometimes be pushed into, be pushed quite far into making the statement more general. Okay, but at the very least, this is a statement that holds, that is proven like this. Okay, so this is what we proved. Maybe I will check until next time what is the most general statement of a residue here, or maybe that's not. It is not really of great interest. We will see. Okay, so of course the proof of this in this statement is exactly the same. It's just that you say that you can deal with these poles one by one. Okay, so of course the remark is to deal with more than one pole. In the proof, you can consider, so if you have such a gamma and you have several poles inside, so let's say you have two poles inside, A1 and A2, then you know you can always do this thing where you look at some smaller curve, and then you look at some smaller curve here, and you can treat them individually. So we have already said many times what it means when I draw such a picture, right? So I don't have to go through this now. Okay, so yeah, so the sum of the integrals here is equal to the integral along the curve by Cauchy. This is what I mean. So let's see some examples. So I will erase it now. Let us recall. So, okay, first of all, so for essential for essential singularities, it is often hard to compute the residue. But now I wrote down the residue theorem as though with a statement that is not valid for essential singularities. So let me go back to that point next time. Sorry about that. So for poles, let me just recall you this. For poles, we have some tricks to compute. I mean tricks. It's just very easy. computing the residue is very easy, right? So do you remember how we can compute? So let's see, for poles of order n, let's say it's order n. So how can we compute such a thing? So first, if n is equal to 1, we have an extra simple formula, right? So then if n is equal to 1, it means that we have our function f of z has a power series expansion which is of this form. Okay. Maybe it's a bit silly that I call this one a and all these a, but okay. Plus a0 plus a1 g plus a2 squared, etc. Okay. So now we see that if I take z minus a, f of z, then this is equal to a minus 1 plus a0, oh sorry, z minus a. Okay, plus a1, z minus a squared, and so on. So now what happens is that the residue of f at a, how do I get rid of all these extra terms? Well, I can say that it's equal to the limit as z goes to a, z minus a, f of z. Okay? So, I mean, of course, if I already had the power series expansion, I could just read it off here. But, and this is what you essentially have to do for essential singularities, but for poles of order n, you can do something like this. So if n equal to 1, you can do this. It's the simplest case. You just take the limit here. So if n is, so it's possibly greater than 1. So then you have a formula that. So of course, if we had many terms here, what we want to do is we want to multiply by z minus a to the n. Okay, but then we also want to differentiate away some terms. So it's equal to, and you can prove the following formula basically. So n minus 1 factorial limit as z goes to a, and you take the differential n minus a times z minus a to n f of z. Okay, so you have this formula in general. Have you seen this formula? Yeah. Good. And then 2, so you also have this trick that if f is quotient p over q, where p and q are analytic at a, and okay, p of a is not 0, and q has a simple, okay, so simple pole, I haven't formally introduced this term, so simple pole means that the order of the pole is 1, okay, simple pole means order 1, okay, so it has a simple pole at A, simple 0 in this case, of course, but a simple 0 will mean that the 1 over q will have a simple pole, okay? But q has a simple 0. Then, so I suppose you are seeing also this formula then. So then, the residue of this f of p over q at A is actually equal to p of a divided by q prime over. Okay, and then you have, so if this 0 of q is not simple, so if you have a multiple, so if you have a higher order pole of 1 over q, then you can get this kind of formulas, but they are much more complicated. Don't know if you know it. So for example, if q has a double 0, so q a double 0 at A, then already the residue has some more complicated expression. 6 P prime of A, Q base of A. This is not something I know by heart, I can assure you. 2 P of A can derive 3 times, and we divide by 3 Q base of A squared. So you see the formulas get much more complicated quickly, but it could be interesting to know that they exist. And you can do this also for n equals 3 and so on, but this is not something you would want to write down. Okay. So, examples. So, of course, one of the main applications. Okay, now you can integrate along closed curves. You can integrate complex valued. You can integrate functions, even meromorphic functions. Okay. So, but you can also have these applications to real integrals, which is something that simply goes hand in hand with what we're doing with the complex integrals. Because, I mean, it doesn't even have to be a real integral. So here you have a complex plane, right? And so if you have an integral, you're interested in an integral along some curve, so it could be along some interval here on the real axis, or maybe the entire real axis. If you're interested in this, well, then you say, okay, let me take this as part of my curve and make it a closed curve in some way. The standard way is this. And then you say, okay, now we can compute this using the residue theorem, and then we get some result, and this result is the sum of the integral I want and this extra part. And then you evaluate the extra part, and then you get also the integral you're interested in. So this is the philosophy why this is usually applied to real integrals. But of course, you could do this equally well by, if you were interested in computing an integral along something, and then you could just make it a closed curve, and you could compute the integral along both these, so gamma 1, gamma 2, and you could just compute, so if you knew how to compute this additional part somehow, then you could get the result also for gamma 1 using the residue theorem. But of course, this is hard in general, but for real integrals, you can easily do this. In a nice way. So let's recall how you can do this. So, I mean, it's particularly interesting because you have these real integrals, such as the one I'm about to write down here. So this one, you cannot solve it by means of elementary calculus. So you know, I'm sure you have heard that there are such examples, right? Of integrals that you cannot solve by basic methods of calculus. And this is one of them. So, but you can show using the residue theorem that this is equal to pi over e, okay? But this is not possible by usual calculus techniques. So this is an integral that arises in probability theory a lot, okay? X squared plus 1. And the way you do this is exactly what I was drawing earlier. So you consider this segment from minus r to r on the real axis, and then you want r to go to infinity to get this. Because of course the definition of such an integral is the limit of the integral from minus r to r as r goes to infinity. So you do this, you look at this semicircle here. Okay, and you call them something. So maybe you call this part CR, and you call this part, what do we call it? Let's just call it minus R to R. Let's just write it this way. So then what you get is, of course, that, okay, so I should also say that you consider this complex valued function instead. Okay, which we integrate along this curve. And then this has poles. What are the poles of this function? Okay, so it's plus minus I. So we have I inside here, and then the other one is outside. So we only need to care about the one inside, because here the winding number is 0. Okay, so we care only about this. Okay, I'll do this a bit quickly since I think you already know this, it's just a matter of remembering. So then, so you look at the residue of f at I, and what is this? Well, it's equal to the limit as z goes to I, because this is so these are simple poles, okay? So order 1. So this is the limit as this goes to I. Okay, so it is equal to e to the I z over z plus I evaluated at z equals to I. Because of course what I had was this function, this is z minus I times z plus I. So when I multiply by z minus I, we cancel and we get this. Okay, and this is equal to e to the I squared, but I squared is minus 1, so e to the minus 1 over 2I. Okay? So you get that. And then now by the residue theorem, what we get is that this integral along CR plus this, so you often use this, it's it's customary to use this addition symbol for curves or arcs, which simply means that I follow first one of them and then the next one. Okay. So this is what this addition means. So this is the closed curve, which consists of both these parts. This is equal to 2 pi I times the residue of f at I, which is equal to 2 pi I times 1 over 2I times the inverse, okay, which is equal to pi over e. Okay? It is equal to pi over e. Good. And now, to conclude, we claim that integral of CR, so it's interesting that this is independent of R, right? Okay?
Or R greater than 1.
Sorry?
R greater than 1.
We need R greater than, yeah, sure. So independent of R greater than 1. So of course, you already imagine that R is a very, very large number. So it's an arbitrary, very large number. Contains this. So CR, but thank you. It's a good remark. So this thing of f of z to z, this tends to 0 as R goes to plus infinity. Okay, so this is your mark, and you show this using the so-called Jordan's lemma. So this is probably the most important part for you of this exercise, because I think everybody remembers this. This is a very standard application of the residue theorem. So next time we will do much harder things, much trickier things. Like, even this translation from here to considering this function, it is not always that you just exchange x for z. Sometimes you look at something completely different. Okay. But this is a very straightforward application, so there are no branch cuts or nothing. So this is easy. But then I just need you to remind you what you do to estimate such integrals and showing that this goes to 0. So does everybody agree that we would be done if we do this? Okay? Because this integral depends on r, okay? And we are interested in the limit of IR as r goes to infinity. And then we would get the integral that we want. So, yeah, we want to prove this claim. Then we have the Jordan's lemma, which says that if alpha is some real number greater than 0, and MR is the maximum over such an arc, okay, minus r to r. So it's always concerned with such things. So if m is the maximum over this of g of z, then the integral over this, so let's call this CR, right? So then the integral over this CR, g of z, e to the I alpha z dz, its absolute value is less than or equal to pi over alpha times MR. Okay? So we are going to use this. And in the application, so how do you apply this? So this means that you want, so if as long as you're integrating something that is of this form. So in our case, g of z is 1 over z squared plus 1. Okay? And then the maximum of this, you can see that this is bounded by 1 over r squared minus 1, which is something that will go to 0 as r goes to infinity. So you have this and you want to apply it. That's okay, my time is up. So next time I will prove this lemma and I will just finish the example. We'll call this, because this one is used time and time again. Then we'll see some more difficult parts, and then we'll see some more theoretical applications of the residue theorem, like argument principle and all this counting 0 business. Okay, so let me stop.